Hello, everyone. So let us continue our discussion. In the previous video, we looked into the effect of intensity in the like in the analysis of the IR spectrum. So today we will just look into like what is like how to decide the position or how to understand why a particular absorption band is coming as a particular lower frequency and some of the absorption bands are coming at a higher frequency. What decides that factor? Okay, so today we'll be discussing only one factor. Okay, so in this discussion we are going to see position and shape of the absorption band. So the first important criteria on which the position depends upon shape I'll discuss in the coming videos. So first factor that determines the position of, uh, of, of a particular absorption bands is dependent upon the Hooke's law. So if you would have gone through your complementary physics classes, you might have seen the action of springs. So when we started the infrared spectroscopy, I told you that you can consider the bonds to be like springs. They are always in a constant motion. So we can apply the Hooke's law here as well to any particular bond. So if you look at the Hooke's law, like this has been converted to calculate the wave number. Okay, and it's proportional to the frequency. So wave number is nothing but equal to 1 by 2 pi c root of k upon mu, where k is your force constant. That means the stiffness or the strength of the bond. Okay, and mu is nothing but the reduced mass, which is m1 m2 upon m1 plus m2. So if you now see the frequencies, like which factor does it depends upon, there are two factors on which the frequency depends on, or the wave number. Because in this case, frequency and wave number, they are proportional to each other. So this frequency is is directly proportional to the force constant. So that means if your bond is stronger, it would give a higher value for the frequency. And if your atoms, okay, that are attached to the bond are kind of light atoms, that is mean they have a lower mu value, then obviously also lead to a higher frequency. So there are two factors that lead to a higher frequency. Either your k value is high or your mu value is low. Okay, because it's in the denominator, so they are inversely related. So if mu is low, it will lead to a higher frequency, and since the frequency is directly related to force constant, so if k or the force constant is high, it would lead to a higher frequency. So we can shortly say that a stronger and a lighter atoms lead to a higher frequency in the absorption band that are appearing in the IR spectrum. So just to compare now, if you talk about C triple bond C, C double bond C, and C single bond C, you can see that we understand that as the bond order increases, the strength of the bond increases. That is a pretty plain fact. So C triple bond C is a kind of stiff bond, or they are strong bond. So according to Hooke's law, we expect K to be higher for a triple bond. So therefore, we should expect it to have a higher frequency. And that is why you can see that the value of the wave number is coming to be 2150 centimeter inverse. Here I haven't written the unit because in IR spectroscopy, it is kind of understood that these values are reported in centimeter inverse. Okay, so while you write in the examination, please write centimeter inverse also. You just don't write the values, but along with it write centimeter inverse. It's the usual practice of writing in the examination, but for convenience sake I haven't mentioned the units here. But always remember, these values that I'll be reporting here is all in centimeter inverse, because we are always reporting that value in wave number. So accordingly, you see C triple bond C is 2150, C double bond C is 1650, and C single bond C is 1200. Very much in line with this particular Hooke's law, where as the force constant is decreasing, the value of the frequency also keep decreasing. Okay. Now let us consider these particular molecules. So CH bond, we have CC, CO, Cl, CBr. Here there is no much variation in the bond order. Basically, they are all single bond. But you see, still we have a huge variation in the value of the frequencies. So that is now decided upon by the mu value. So this is lighter, this is pretty much heavier than this, then this is more heavier, more heavier, more heavier, and it's the heaviest. So as the mu value increases, again you will have a reduction in the frequency because they are inversely related to each other. So you can see that the values are kind of matching with the way that is the Hooke's law. It's like obeying the Hooke's law. Okay. Similarly, you can see here the C triple bond, that is cyanide, and the C double bond N, that is imine, and this CN bond. Okay, you know that bond order is higher or force constant is higher for this, so it should have a higher value. So pretty much in agreement with the Hooke's law. You see the values here for the frequencies that appear in the infrared spectroscopy. Okay, now what I would like you to do is, here I have given you three CH bonds, and they have different values. Okay, so I would like you to get hold of some organic book and find out the value, that is the wave number at which these CH bonds appear in the infrared spectroscopy, and then tell me why these values are behaving in a particular fashion. So that is your work that you're going to do and would be reporting in the live session. Okay. So I hope you understood that how the appearance of the peaks in the infrared spectroscopy, in the infrared spectrum, is decided upon by this important law, that is Hooke's law. Okay, so this is one important factor on which the position of the absorption band is decided on in an infrared spectrum. Okay, in the coming class, we'll be discussing more about the various factors that decide on the position as well as the shape of the absorption bands. Thank you very much for your kind attention.